just for the video's sake, because we lost the audio for a little bit, we're comparing the heat of formation and the heat of reaction methods. Here are the energy balances, and we're building a table, and we'll move on from there. All right, so not the highest quality video that we've produced. So, we can make this problem arbitrarily complex. Every single one of these reacting species could be entering and exiting at a different temperature. In a real process, you probably wouldn't want to have the methane at 1,000 degrees. That's a bit of a high temperature flammable gas you really necessarily want to deal with. And having the inlet and the outlet be at exactly the same temperature is going to be relatively uncommon in a chemical process. If it's an exothermic process, you're generally going to be feeding in your reagents at a much colder temperature, because as the reaction progresses, it gets it up to that ideal conditions pretty readily. So you don't have to spend the energy to preheat it. If it's an endothermic process, you might want to preheat your material so that when the endothermic reaction goes on, it'll cool it down. But for an example, we're just going to keep it at 1,000 to make it nice and simple. But we can have these totally different for every individual species. All right, for the heat of reaction method, we have a different energy balance where we have all of these individual terms here corresponding to the extent of, corresponding to the reaction at the standard state. So these terms here will be different based on the reference. So here a reference, of course, is the molecular state at 25 degrees C and 1 bar. For the most part, we don't have to worry about the 1 bar because we're not super diligent on calculating enthalpy changes of material as a function of pressure, but we say 1 bar here just to remind us that this is at sort of room temperature pressure. Is it going to be a liquid? Is it going to be a gas? Whatever the case is going to be. All right, so for the heat of reaction method, every single thing that we put in here, every single number, we have to go calculate the delta H of the material going from the reference state to 1,000 degrees Celsius. So we're going from a molecule at 25 degrees C to a molecule at 1,000 degrees C. This is just equal to the enthalpy at 1,000 for species I minus the enthalpy at 25 degrees C for species I, which we call the reference state, which is 0, which allows us to relate this delta H that we're going to write down to the actual number that we're going to plug into the table. And this will just be integration of 25 to 1,000 C sub P for species I dt. So if you were to build this table in an Excel spreadsheet, and I do not recommend that anyone does these calculations by hand, build them in a spreadsheet. What I would do is I would have a second table just above this one in exactly the same order. Material properties for methane, material properties for water, material properties for CO, and material properties for hydrogen. You would need to input heat of formation, A coefficient, B coefficient, C coefficient, D coefficient for heat capacities. Then for every single one of these cells, I just input one equation, and then I copy and paste that equation for every single one. And the only thing that's different is the heat of formation values, the A, B, C, D coefficients for the heat capacity correlations. So when you build your table really coherently and organized, it means that you really only have to do this one thing. This is all of the analytical input that you have to do with the balancing of a reacting system. Yes?
But if they are, like in the case of a reaction where they're not all vapor, then you'd have to put in they'd be slightly different, right? They could be slightly different. Like one reaction could be, like one reactant could be a gas, and the other one will be a liquid or something. And you have to get them.
Yes, so in the case of water, for example, let's say we didn't use the heat of formation for gas phase water, and we used the heat of formation for liquid phase water. This formula then would be different. We would have to, heat it up to the boiling point, vaporize it, and then heat the vapor up. But for water, in this circumstance here, we can actually go straight to forming it as a vapor. Let's say, for example, the inputs and outputs were not at exactly the same temperature. We could just modify our table here to add in a column of the temperature that each species is being fed at. So instead of using one uniform value that you might have in your spreadsheet somewhere to refer to as your temperature of the reaction, right, because you're calculating your delta T, you could have another column here that says T in and T out for every individual species. You could do that as well. And so instead of referring to the 1,000, you would refer to the feed temperature of methane, the feed temperature of water, and so on and so on. Okay, and then the only other step here for the heat of reaction method is that the standard heat of reaction is just going to be the summation of all of the formation reactions. Right? Products minus reactants. How much energy do you get out when you destroy all the products, and how is that compared to all the reactions? Or the reactants, sorry. Okay.
I've got a question on that.
Yes.
Maybe I'm not understanding the form or like this approach.
Mm-hmm.
So when you're heating the water vapor from 25 to 1,000,
Mm-hmm.
is it just because we're setting the reference state that we don't have to worry about this like the liquid state, or like it's just confusing that you go from 25 to 1,000? I guess.
Right. Okay. So you're saying that in this reference state here, this is 25 degrees C in 1 bar. It should be liquid water, but we're kind of skipping over that step.
Yeah.
And this is where it's kind of really useful to sort of talk a little bit about the heat of formation method as well. Since we are treating the reaction itself as all gas phase, if we were to calculate the heat of reaction using either liquid water or vapor water, we would have a different value. We can choose to do the reaction based on having liquid water, or we can choose to have it based on vapor water. In this case, it makes a lot more sense to have it be vapor because that's what the final state is going to be. But if you could just hold on for just 5 minutes, let me do the comparison to the heat of formation, and I'm going to show you that the math works out exactly the same. Yeah.
So the heat of reaction method, you still have to find all the include all the heats of formation.
Oh yeah, it depends on how you organize your data. But the numbers are exactly the same. The amount of work is exactly the same. It just depends on how you want to think about organizing things.
So you find that each of the H hat,
Mm-hmm.
and then you also need to find the heat of reaction through summing up all of those guys.
Yeah.
And then in the original formula, you need both of those to solve for. Or no, I guess that is H.
Yeah. So I'm gonna hold off on that one for just let me wrap up and move on to the heat of formation, and then I'm gonna write them in a way that it shows that they're exactly the same thing. So in the heat of formation method, so our reference state here is the atomic species at 25 degrees C and 1 bar. So same approach. We want to go from the reference state to 1,000 degrees C. So in this case, right, same logic applies here, so we can get an actual number. We just have to add in an additional step. Oops. We are first creating the compound, and then we are going to be heating up the molecule from 25 to 1,000 C sub P dt. Right, so that's a reference. So our reference is all the atomic species, and so we create the molecule from a chemical reaction, then we heat it up, the molecule, to our reference state. So now let's do a comparison of the two approaches. So I'm going to write out the energy balance. I'm going to write out the heat of formation energy balance, and I'm going to organize it so it allows us to see the parallels between the two. So the number we're looking for here is Q, either the heat in or the heat out of the system. We're going to write it as the summation out minus everything coming in. And I'm going to go species by species. So we have 1 methane. Sorry, my bad. 1 CO, out minus in. Okay, that's our reaction. 1 CO times by the heat of formation of CO at the standard state, plus integration here from 25 to 1,000 of the heat capacity of CO. Plus, we're producing 3 hydrogens. We have a heat of formation of hydrogen gas. Right, this term is 0 because you're at the reference state. The reference state is pure hydrogen in the gas phase. But if I were building this in a spreadsheet in my computer program, I wouldn't change this formula. I would just put a 0 in my table that has the heat of formation for hydrogen. And if you really want to make your table even more general, you don't actually input your numbers for the equations here. I would add another row that tells me what the stoichiometric coefficients are for each of my species. So when I build my reactions, I don't actually input any numbers into my equations. Right? I hold true to that philosophy. I would just add here methane stoichiometric coefficient, water stoichiometric coefficient, CO stoichiometric coefficient, hydrogen stoichiometric coefficient. And then I have even less input involved. And then when it comes to solving for the in versus the out, I have an extensive reaction term up here relying on the stoichiometric coefficients, and then I build the whole reaction into the system that way. All right, so I'm going to continue here. So now we're minusing the inlet, so minus 1 CH4 times by its heat of formation. And the last piece is the water, minus 1 water. In this case, I'm going to say gas phase, right? Okay, so I'm adding all of these together. In this case, you could think of it as adding a negative. So, all of these terms right here, this is just equal to the summation This is just the standard heat of reaction. We have stoichiometric coefficient of CO, positive 1, positive 3 for hydrogen, minus 1 for methane, minus 1 for water. That is the summation of the stoichiometric coefficients times by the standard heat of formation, which is exactly the heat of reaction. These terms on the right-hand side, this is the calculation of delta H going from the reference state to the final state for the heat of reaction method. So all that we're doing here between the heat of reaction and the heat of formation method is, do I want to draw a line in my energy balance and say, no, that's not the heat of formation, so we're going to call it the heat of reaction. And then on this side over here, it's just the reference state for the heat of reaction method. Does that make sense? So it's exactly the same thing. So to answer some of the questions about, when we're calculating the heat of reaction or going from the reference state, do we want to choose liquid water or gas phase water? So here, it all depends on what you consider that you're creating. So although water will want to be at a liquid at 25 degrees C and 1 atmosphere pressure, we can sort of create a hypothetical water that's in the vapor phase at that conditions. And the only thing we have to add into is the heat of vaporization. Does this help clarify the differences between the two approaches? Yes?
Why do you need an extent of reaction in that equation?
Oh, yes. So in this case, the extent of reaction is 1. So it works out here. So in this case, yeah, the extent is 1. So if we added in the extent here, this would be equal to extent times delta reaction. It just works out, so it's fine.
So would you have to solve for those extended reactions beforehand, or
Yes, in general.
in general?
But you could envision a situation where you did not necessarily know how much the reaction progressed, but you measured how much heat came out of it. So you could think of it backwards like that. In general, the standard reaction balance, you will have to know the material balance first before you can solve for the energy. But you could, of course, envision a scenario where you knew the energy in or out and you had to use that to solve for the material balance. Right? Because the material balance is built in. Right? The material balance is built in with these n terms here.
Right.
So we can make these problems as arbitrarily difficult as we want. I could say, you measured a megajoule per hour coming out of this system. How much of the reaction occurred? And that's something you can envision possibly happening, yeah.
I'm still a little confused.
Mhm.
So the ultimate equation you ended up with is the equation for the heat of reaction approach.
They're the same equation. It all depends on how we want to organize our thoughts. Do we want to think of, so in the heat of reaction approach, what we're thinking of is we're keeping track of the energy coming in from the methane and water and the energy coming out in the CO2 and hydrogen, and then the reaction is either releasing energy or consuming energy. That's sort of how we're thinking about it in the heat of reaction approach. In the heat of formation approach, we're treating it as the methane brings with it all of the energy, including the energy of its chemical bonds. And the CO and hydrogen, they leave with all of the energy, including the energy of their chemical bonds. And in the heat of formation method, we don't even consider whether it's endo or exothermic or anything like that. We just know how much total energy comes in, how much total energy leaves. But in the delta H of reaction method, we treat everything sort of as a non-reacting system, and then there's just sort of this spontaneous source of energy, either from an endothermic or an exothermic reaction. Yes?
So in the case where the extended reaction isn't one,
Mm-hmm.
you'd have those stoichiometric coefficients like modified by the extended reaction somewhere.
So in this particular example here, if we wanted to take it one step further, the n dot flow rate, the flow rate of each species in and the flow rate of each species out, that would change. So if we had a system where that wasn't going to completion, it wasn't super well organized in terms of the stoichiometric coefficient, these numbers here would change. And so what you would get then is that the stoichiometric coefficient times by these would all work out to how much of that reaction actually goes on. So if we have, let's say, only 50% completion, right, then when we have, only half of the methane would react, only half of the water would react, we only get half as much of each of these two once formed. In which case we would simplify it, and we would say 0.5, 1.5, 0.5, 0.5, and then in that circumstance the extent of reaction would be 0.5. And so the math would all work out perfectly fine in that situation again as well. Yes?
Sorry, so the delta H of the reaction is equal to, so it's equal to all that, right? So that's your,
Delta H of reaction. So this is just a definition, right, based on the sum of the stoichiometric coefficient times by the heat of formation.
right,
Yep.
and that's all,
That is these terms here. 1, 2, 3, 4. That is your heat of reaction. Or rather, how much energy is released as a result of the reaction itself. From the chemical bonds to temperature sort of energy, I guess. Right, because a molecule can store energy in a number of different ways. So if we give a molecule a bunch of energy and we say, you can only change your temperature to store that energy, that's dealing with these terms right here. So what we're effectively saying is, we're taking some energy that is currently stored in the form of a covalent bond. This term right here, the stoichiometric coefficient times by the heat of reaction, that tells you how much energy is being released or absorbed in the form of a chemical bond. That energy then has to be transferred into it could be transferred out of the system, Q, or it could be transferred into the temperature of the system themselves. And that's actually what I was hoping to talk about today in the form of an adiabatic reactor if we get to it. But I'd much rather we resolve a lot of these questions here about the two methods. Because this week's homework is like 4 questions on energy balance systems. But I promise you, if you build your spreadsheet well, you can basically use the same spreadsheet for all the questions. It's just modifying what is the reaction, what are the properties, what are the states of matter. So one spreadsheet, if designed well, all you need to do is resave it for each of those 4 problems and just change the material, the stoichiometric coefficients, and all that. So they're all basically the same type of problem, but we just need to get it to click solidly once.
And can we use the delta H formation for all of them? Or
Oh yeah.
Okay, so we're not, I haven't looked at it yet, so we're not constricted.
I think you have to. So the one instance here, right, though, is that for simple reactions like this, where the compounds are all very well characterized and very well studied systems, heat of formation method is going to work phenomenally. Now, the only circumstance where you would have to rely on something like this is if it's a more complex reaction where we don't necessarily know the formation energies, we just know the delta H of reaction. So if we don't know the formation energies for everything in the system, we physically cannot use this term. Right? But if you're given the heat of reaction of some process, and maybe they didn't even bother to measure it at the standard state, maybe they measured it at some different state, then you would be forced to think about the problem like this. But if you had an infinite amount of data, then the heat of formation method is probably the best way to go. But there may be special circumstances where you don't know all the formation reactions for all the different processes, and you're only given a heat of formation, heat of reaction at a certain set of conditions. Okay. So, let me move on to one last topic just to introduce it, and we can cover it a little more. And that is the concept of an adiabatic reactor. What does adiabatic mean? Q is equal to 0. Q or Q dot is equal to 0. So let's say, for example, we have a methane combustion reaction. And I am feeding a, let's say, Bunsen burner in the laboratory. So I have one CH4, one O2, in this case, let's just say it's moles per second. And leaving, I have my 1 CO2 and my 2 H2O. I'm going to say this T in is at 25 degrees C. So imagine that I have a burner, like I said, a Bunsen burner just sitting in the lab. You have a natural gas feed line. It's grabbing some oxygen from the atmosphere. And out here, we don't know what the temperature out is, but we're calling this an adiabatic reactor so that Q is equal to 0. In the adiabatic reactor, we are effectively saying that all of the energy that is either consumed or released by the chemical reaction has to be distributed into the individual species in the system. So in this circumstance, what we're doing is we are breaking the CH bonds, breaking the OO bonds, and we are forming CO bonds and HO bonds. These are a lot higher energy than these ones over here. So all of the energy that is released by breaking those covalent bonds, not all of it is needed to reform these ones here. So we have a surplus of energy. There's 2 options. We can pull it out of the system and control the temperature here, or we can figure out how much that energy goes into heating up the product species. Now the complication here is that these can be sort of complex nonlinear problems. If we were to think about our table that we had constructed here, and sometimes I really think it's useful to understand the problem to think about how we solve it. In this particular instance here, what we would be doing is we would have a cell in our spreadsheet. that's set to 1,000 degrees Celsius. This is our outlet temperature for the steam reforming reaction that we did. In that process, we can calculate definitive numbers for every single enthalpy in and enthalpy out for all of our species because we have access to the data tables. Then we add all up these terms. The imbalance of the enthalpy in and the enthalpy out tells us what our heat requirements are. And so at the bottom here, you're going to have some number here for the summation of NH in, summation of NH out. And the difference between these two tells us our Q. That's what we're calculating here in our energy balance problems. But we can take this exact same tool if we designed it right. And what we can say is instead of knowing that our outlet temperature is 1,000 degrees C, we can solve for it. And then the criteria would be to match that the enthalpy in is equal to the enthalpy out. That tells us that no heat is entering and no heat is leaving the system. So your Excel spreadsheet or your MATLAB code, if you've designed it effectively, you can then just manually vary this until these two terms approximately balance each other out. Or GoalSeek, or Solver, does that process, but in an automated fashion. So the adiabatic reactor is conceptually no more complex. And practically, it's no more complex if you design and you organize your calculations in a very well organized and regimented way. But, for example, if you take this 1,000 and you put it into your spreadsheet, 1,000, 1,000, 1,000, 1,000, 1,000, that means in order to switch from being an adiabatic process to a non-adiabatic, you have to manually go in and guess and check and change every single cell and every single calculation here. But if you organize it such that you never put a number in an equation, right? That's my recommendation, my philosophy is never put a number in an equation. In MATLAB, in Excel, in anything. Always define it so you can know exactly what it is and then refer back to it. Because computers are much better at substitution than I am, and I suspect are better than most everyone else. Right? I'm really bad at making math errors. So, we don't have a chance to go through the rest of the solution here, but we'll go through it on Wednesday. But the short end of it is that we're going to be calculating in this problem called the adiabatic flame temperature. Essentially saying if I mix methane and pure oxygen and I burn it, and I'm not allowing any energy to leave the system, how hot will my product gases get? Any guesses? How hot do you think it would be? Everything comes in at 25 degrees C, and all of the energy that's stored in those chemical bonds goes to heating up CO2 and H2O. How hot do you think it'll get?
Like numerical value?
Yeah, numerical value. Like 100 degrees C, 200 degrees C. What do you guys think?
800 degrees C.
We have 800. What else we got?
635.
You guys are all extremely low.
2,000.
Higher than 2,000.
5,000.
Higher than 5,000.
10,000.
Lower than 10,000. It ends up being 7,800.
That's just too much.
Now this is for O2. This is burning it in pure O2. But to give you an idea, right, that tells you how much energy is stored in a covalent bond. It's a lot. Right? So if I break all of these covalent bonds and I form these ones here, that imbalance in difference in energy is enough to heat these gases up to 7,800. Now if I were to repeat this in air, would it be higher or lower? Lower. How much lower?
5,000.
80%.
That's a lot lower. It's 2,200. Right? So these things get really, really hot. There's a lot of energy stored in chemical bonds. Yes?
Where does steel melt?
Steel. I don't know. Good question.
Do you have like,
Well, the temperature of the sun is 5,000. The temperature of the surface of the sun is 5,000. Something 5,500 degrees.
So these are idealized calculations. So of course you are going to have heat transfer leaving the system extremely rapidly.
Yeah.
So when you have flames this hot, they're all going to be, you know, radiating energy massively. And that's most of the heat transfer that you deal with when you have a flame. Is you put your hand in front of a fireplace or the stove or something like that. A lot of the energy is being transferred by radiation. So these are idealized calculations. Of course, you're never going to get these temperatures exactly. But it gives you a good concept that if you were to burn your fuel in pure oxygen, that's how you get to a much higher temperature. And so in terms of one of the technologies that they have for clean coal, for example, is called oxy-coal combustion. So if you can burn the coal at a higher temperature, then in theory you can run your process at a higher efficiency from the Carnot cycle, and you get better, more complete combustion. And you don't have to deal with any nitrogen when you're trying to separate the CO2 that you can then subsequently sequester. Yes?
Any idea of how hot it would be with the hydrogen?
Oh, so that would be the adiabatic flame temperature of hydrogen, and I don't know what it is off the top of my head. I suspect it would be significantly lower because you have much less. Well, I don't know, because you're forming. Because hydrogen, you're forming less product gases, so there's fewer bonds to absorb the energy up that way. But I think hydrogen has a lower energy density than methane does. Well, because it has more bonds. But whether or not hydrogens, if you took methane and divided it by 2, because really you're breaking 4 bonds here, and in hydrogen you're breaking 1. I don't know. But it's a relatively straightforward calculation. But we'll set this up on Wednesday. Yeah.
So just to clarify, so on this type of problem, we're really just, it'd be like a non-linear solver in the case of like a MATLAB?
Well, so if you assume a constant heat capacity, you might be able to set this up as a linear problem. But if you're solving it using correlations for your heat capacities for your outlet, then it'll definitely be a nonlinear solver.
Can you repeat that, sorry?
So if you do a non-constant heat capacity, which you definitely should do, you would have it has to be nonlinear. Right, because the T out, it would be like T out to the 4th power minus T in to the 4th power. And you'd have all of those for all the different species. So it's a big problem. Yeah.
Yeah, but so let's just assume CP's constant. Then it's just a simple T out minus T in. And it's just going to solve all those.
Yeah, exactly.
I was gonna be like.
All right, for those of you who are remaining, take care.